Okay, good morning, everybody. It's always good to see you. Okay. I sincerely hope the feeling is mutual. Okay, the topic of this part, the course is we want to talk about block diagram. Now, what is a block diagram? Block diagram, as illustrated here, is a graphical representation of control system structure and signal flow. So as the name implies, a block diagram is made of blocks, a number of blocks. So what is a block represent? It represents a subsystem or a component of a control system, often modeled by its transfer function. So within every block, we have a subsystem, and that subsystem, the mathematical model of that subsystem is transfer function. So the manipulation of the block diagram apparently is on the X domain. Okay, we do everything about block diagrams in X domain after Laplace transform. Okay, and what do we want to do that? By using block diagram, we can analyze and design the overall system behavior efficiently through visual and algebra means. Okay, because with Laplace transform, we convert differential equations into algebra equation. And more importantly, with a transfer function model, the output of a system and the input of that system can be connected by a transfer function. View a very simple, straightforward mathematical operation, which is multiplication. Therefore, block diagram bridge the gap between physical system components and their mathematical representation. Okay, there's a gap between a real physical system and a mathematical model. Okay, apparently they are not the same things, although they represent the same entity. Okay, so how do we bring these two things together? One very bright idea is to use block diagrams to help us understand the interactions between each components. And okay, so through transfer function, block diagrams allowing engineers to model, analyze, and design control system systematically. Now, we all know what a system is. A system is actually consists of three components. The system itself, its input, and its output. And these systems can be connected in several ways. The first possible configuration is in cascade form. Let's say we have two subsystems, or simply two systems. System one has a transfer function of G1, and the second system has a transfer function of G2. Okay, we we connect them in series, and this is so-called cascade form. All right. So for G1, the input is X1, and the corresponding output is X2. And the output of G1 is actually the input of G2, and the output of G2 is X3. Apparently, G1 represents the transfer function of the first system, and G2 accordingly represent the transfer function of the second system. When they are put into place in such a configuration, we can replot this block diagram in this form. Why can we do that? Because math tell us we can do that, right? Through multiplication. Because you know the connection between X1 and X3, that is the ratio of X1 to X2 is actually this. And how do you get this? You multiply G1 with G2, right? And this is what you will get. this part is G1. This part is G2, okay? So the overall transfer function goes from X1 to X3 is actually G, which is the product of G1 and G2, okay? Very easy to understand because the only mass it involves is multiplication, okay? Very straightforward, okay? That is one of the key reasons why we want to use block diagram in the first place, all right? Now, okay, so this is another representation of cascade form. Now, sometimes use cascade form, we can actually decouple the transfer function of a given system. For example, this is a pseudo system. As you can see, it has numerator and the denominator, okay? We can think of the denominator as one subsystem cascaded by the numerator, all right? That's another way to look at the problem. Now, of course, we can connect subsystems in series, we can also put them in place in parallel form, okay? This is one example. The input, or should I say, the common input here is R. And this input is applied to these three systems. Hence, we have three outputs, all right? And by acting them together, okay, they can be acted together, okay, or they can subtract from one another. It depends on which sign you employ. It can be either positive, which corresponds to addition. It can be minus, and the minus sign apparently corresponds to subtraction. And the resulting output, of course, are the algebra result of subtraction and additions. And that is what the output look like. If you want to reduce it into one simple system, then this is the input, this is the output, and this is the corresponding transfer function, all right? Now, here comes probably the most important part of block diagram, okay? This is a block diagram of a unity feedback system. When I say unity, is the output multiplied by 1 or without any further processing, go directly back to this so-called summing point, okay? Here we have positive sign. Here we have a minus sign, which tell us this arrow signal, E, is essentially R minus C. So think of this R, which is the input of this feedback system, R's the target output, R's the command for the feedback system, R's the desired output of the feedback system, command, target output, desired output, same thing, different terminologies. That's it, all right? And this is, of course, the transfer function of the system to be controls. It actually consists of three parts. What are they? Controller, actuator, and the entity we want to control, or the process we want to control, all right? And this is the feedback loop. Now, here, what is the question here? The question here is, how do I determine the transfer function go from R to C, okay? We can do it with the assistance of block diagram, okay? Now, before doing that, I want to emphasize this is really a simplified or sometimes oversimplified plot diagram for feedback control system. A real feedback control system typically has this structure, okay? Here we have the input before entering the closed loop feedback loop. It actually has to be processed by so-called input producers. And this apparently is a controller. Plan, as we said before, actually consists of two parts. The first part is actuator, all right? The second part is the system, the object or the process we want to control. When we put them together in cascade form, okay, or we connect them in series, we call it plan, okay? So the transfer function of plan is actually a product of the transfer function of the actuator and the transfer function of the system or process we want to control. And here we have an output, and you need an output transducer to measure the output and then send it to the feedback loop. Here, the feedback represents we have a transfer function subsystem or transfer function here to process the measured output, okay? Let me make more remarks about input and output transducers. Our first, the first thing we want to study here is input transducers. What do we need them? Okay, what do? They convert, let me put it this way, an input transducer converts the reference input into a compatible signal for comparison, okay? So you have a command, you have a desired output, you have a target output, you can also call it the reference input, okay? Now, we want to convert it to a so-called compatible signal for comparison because you need to compare your input with the output. And what do we mean by compatible signal? Let me give you an example, such as converting a physical reference, for example, temperature, position. The target output for air conditioner is temperature, okay? And for a servo control system, the target output can be a particular position, okay? And that is our target output. But in a real control systems, which is often made of digital components such as microprocessors, microcontrollers, such as computers. And for those digital devices, they only receive electric signals. So somehow you have to come up with a calibration scheme to convert temperature into electric signals, such as voltage or current. For example, temperature ranges from 10 degree to 100 degree Celsius. Convert to voltage ranges from 0 to 5 volts because it is the voltage that drives the control system, the control hardware control system, okay? Let me give you another examples. A potentiometer, which looks something like this, convert the desired angular position into a voltage. When you, for example, want to set up the speed of the fan for air ventilation, essentially you use a switch to determine the level of the speed of the fan. And that is so-called an angular position. And you need to have a pre-designed calibration scheme to convert different angular positions into different level of voltage, such that voltage can be used to drive the motor of the fan, all right? So that is the reason why in a real physical control system, we need to have an input transducer to finish this job of so-called converting the reference input into a so-called compatible signal for comparison, okay? Now, what is an output transducer? An output transducer represents the sensor or measuring device that converts an actual physical output, such as position, speed, temperature, into a measurable electric signals. So it is hardware, and that hardware is designed to measure the physical variable, which is under consideration. For example, a tachometer is designed to measure speed, typically angular speed, and a thermocouple measures temperatures, okay? And those devices typically present their results in voltage more often than not. Not always, but usually, all right? So we need a sensor, okay? That is the reason why we need an output transducers to be a essential element of our feedback control system. Now, let's go back to this system, okay? This is a simplified version of a feedback control systems. This is not a unity feedback system. If it is unity feedback system, then H is equal to 1, okay? So this is not a unity feedback system. In comparison, this is a unity feedback system. Okay, so there is a difference there. All right, let's go back to this. Now the purpose here is to determine the transfer function between the input and output, okay? How do we derive such a transfer function? The answer is obvious using information provided by the block diagram. Now, the output from this block diagram is apparently the product of the input and the transfer function, right? This is the output. Now, what is E? From the block diagram, E is actually the difference between R and B, right? Now, what is the B anyway? According, again, to this block diagram, B is the product of H and C, right? Okay, so from here, we have everything we need to connect E with C. I'm sorry, to connect R to C. So how do we do that? Easy. We know E is equal to R minus HX. So we substitute this representation into here, okay? After doing that, see that we get this equation, okay? Now C is actually the product of G and E, which is R minus the product of H and C, right? Okay, so in this equation, we actually have everything we need to connect C and R, right? So let's rearrange the terms. I put all the terms involve C on the left-hand side of the equality, and that will give us 1 plus GH times C, all right? And the remaining term, the remaining term on the right-hand side of the equality becomes nothing but G times R, okay? So this is the transfer function I'm looking for, okay? What is this? This is the transfer function of this closed loop feedback system, okay? So what does it tell us in addition to this so-called mathematical result? It tells us that by using feedback, we can actually change our transfer function, okay? When the system is operated in open loop, the transfer function is G, right? Now, the problem is that transfer functions might not provide satisfactory result. For example, G, let's say it is made of P of X over Q of X. And Q of X is the denominator. And Q of X is the characteristic equation. And the roots of that characteristic equation are actually the poles of the system. And you know, when poles are located in some regions, it may not provide satisfactory or fast enough transit response. Its stability can be questionable. In any event, in the open loop configuration, the poles may located in some undesirable region. How do we change this unpleasant facts? There are two alternatives. One is you use another system. Okay, you don't use this machine. Okay, you buy another machine. Okay, or you redesign that machine, or somehow you alter the machines by yourself, and that is labor intensive. That will cost. It's also very time consuming. So I will have to spend a lot of time, invest a lot of money to get things done. I don't want to do that. I want my life to be easy and simple. So one possibility is that I just accept the system as what it is. I don't do anything about it. However, in using that system, I don't operate it in open loop form configuration. I operate it in feedback loop. Now, by doing that, by using the right edge, okay, I can come out with a new characteristic equations, which means I have the freedom to relocate the poles of the feedback control system. Similarly, I can design the location of the rails, which means now I have a lot of room, or a lot of degree of freedom in shaping the dynamics of the system, okay, to the way I want, okay? It does not mean I can always get what I want, but it does mean that now I have a very powerful tool that can reconfigure or can improve the performance of my system, okay, without changing the machine, the original system, okay? Of course, you have to build a feedback loop, and that is also time consuming. But compared to come out with a new machine or new equipment, usually setting out a closed loop feedback system is much more convenient, much easier, all right? So I want you to remember this result, okay? And this is the transfer function of this closed loop feedback systems. So one of the essential tasks, one of the key challenges, okay, or one of the key missions of control is how do I come up with an edge to satisfy my control requirements, okay? That has everything to do with feedback control design, okay? And that is a main issue of our future study, all right? Okay, now, here I want to introduce a concept which we refer to pick-off points, okay? Which means that, let's say this is the original signal flow of a control system. You have input signal R and goes down into three different paths, okay? One with a subsystem whose transfer function is G. The other is just direct transfer of that signal, okay? You can rewrite this part, replot this block diagram into this manner, all right? What we do is we move G one step forward, all right? And after doing that, in order to this output remain the same, all right? But this pass and this backs, we need to insert or add a transfer function 1 over g here to cancel out this movement of the transfer function, all right? This is what we call pickle points concept. Same thing happened here, all right? The transfer function g can be either here or can be placed here, here, here. In any event, the output of these two systems are essentially the same. They are the sum of RG, I'm sorry, this should be the sum of 3RG, all right? That's it. Now, next, here I want to give you a very, very quick preview of the controllers, okay, that we will discuss in the future. It includes so-called on-off controllers, proportional controllers, integral controller, PI controller, which is proportional plus integral control, and PD control, which is proportional plus derivative controls. And finally, PID control, which is proportional plus integral plus derivative controls. All right? Now, let's first study this on-off control, okay? And on-off control looks something like this, okay? The horizontal axis corresponds to its input, and the vertical axis corresponds to its output. So its output, it really depends on the signs of the opposite, the output arrow, okay? E is the output arrow, all right? Now, if output arrow is positive, then the controller produces and controller output, which has a magnitude of U1. By contrast, if I have a negative output, then the controller output is chosen to be U2. So the controller switches back and forth between U1 and U2. And you can consider the U1 as on and U2 as off. And as we mentioned it in last week's lectures, typically in many cases, we will introduce a differential gap into such an on-off controller, okay? Now, there are some texts here to help you understand more about about this concept of differential gap. But for the time being, let's just illustrate this concept by studying a very simple example. Here, the goal here is to maintain the height of the tank, okay? We all, in many families of Taiwan, we have our oil water tank, okay, for emergency or sometimes for daily users, okay? Now, the purpose is the water inside the tank should be sufficient, okay? But it will not induce, we cannot permit overflow. Of course, underflow is also not desirable. Let's say we have already set up a desired height of the water level, okay? Let's say it is H. If I don't introduce any differential gap, anytime the water level is not exactly H, it will, let's say less than H, then my pump will be turned on, okay? So that more water will come into the tank. And once it reaches H, the tank will go off. But this will happen so often. The pump just keep go on and off all the time. And that can apparently reduce the lifespan of my pump. Okay, so what we do is we introduce differential gap, which means the pump will not do anything as long as the water level is inside this gap. Let's say this gap is H. The upper bound is H minus, let's say, 50, okay, and centimeter. And the lower bound is H minus 50 centimeter, okay? Within that 100-meter range, the pump simply doesn't do anything, all right? So that is the idea of differential gap for on-off controllers. Now, let's go one step further. On-off control apparently is one of the simplest control methods, okay? The other one, if we want to go one step further to make our control action more flexible, what we can do is we can do proportional control, okay? Instead of only two different levels of control operations. Here, the output of the controller is actually proportional to output arrow. So if the output arrow varies continuously with time, the controller output will also vary continuously with time in a completely positive correlated manner, okay? Now, this, of course, is a good idea, okay? And the transfer function of the controller is this, all right? All you need to do, how do we get this? Piece of cake. All you need to do is to take the Laplace transform of this equation, all right? And what you will get is capital U, which is the Laplace transform of this U to Kp to capital E, which is the Laplace transform of the output arrow given in the time domain, all right? And then from this result, U divided by E is apparently Kp, all right? So Kp is the transfer function of a proportional controller. Now here, we can also, let me introduce integral control. Now for integral control, the output of a controller is actually proportional to the integral of the output arrow, okay? Here, T denotes the beginning of the control process, okay? And T means the current time being, okay? We often say embrace the present, okay? And that is exactly what a control system do. It embraces the present. So even in performing integrations, it integrates the output arrow from the beginning to the current time. And Ki is a parameter we need to determine, all right? So as you can see, again, you can take Laplace transform of this equation, and what you will get is U equal to Ki times E divided by S, all right? So if you divide both sides by E, you will get this result, all right? So whenever you see something divided by S in the X domain, it always refers to integration in the time domain. We talked about that before. Now, let's make things a little more complex, okay? Instead of just using proportional or integral control, we can combine it, okay? We can take two different things into considerations. We will not only consider one factor, we can consider two factors, because this proportional control only rely on current information. By contrast, integral control rely on the entire history of the control process, right? When I say entire history, it's not from the beginning to the end. I mean from the beginning to the present time, all right? So the output is actually made of two parts, one from proportional controller and one from integral controller, okay? And this is the corresponding transfer function of the PI controller. Let me emphasize, PI controller is the most popular controller used by the real industry, okay? Most of the controllers you see today in mechanical, electrical, or whatever devices that use feedback control employs PI control, okay? Now, apparently, we can go one step further, okay? If you have proportional feedback, you have integral feedback, why not use derivative feedback? Why do we want to use derivative feedback in the first place? Because the derivative of output arrow represent the changing rate of the output arrow, okay? For example, if the derivative is positive, that means the output arrow is growing, and that is not desirable, okay? By contrast, if this derivative is negative, it means maybe the output arrow right now is very large, but since it is declining, it is becoming smaller and smaller, maybe I don't have to worry that much. So whether it is growing or declining also plays a factor in determining our control, in determining our control actions, all right? So this is the transfer function of the PID control: proportional control, integral control, and derivative control. And in designing such a PID controller, apparently you have three parameters you have to design, all right? You have to specify. You have to find a right set of parameters for PID controllers at the same time, so that satisfactory response from the closed loop feedback system can be achieved. All right. Okay. Now, let me just give you a head up. Okay. For closed loop feedback systems such as this is the controller, this is the plan, this is the sensor, this is the target output, or what we call reference input. This is, of course, the actual output. The point I want to make here is that the reference input is not the only input that is being applied to this feedback loop system. There are another input, which is disturbance. Okay, it will go into the plane in the same way as the controller output. All right. Now, well, actually, it depends. Okay, sometimes disturbance go directly into the process we want to control, or the object we want to control. Okay, so here, to determine the impacts of such a disturbance on the output, what we can do is, or what we need to do, again, is to determine the transfer function from D to C. Okay, so by treating disturbance as an input, and by using block diagram, we can actually determine the transfer function from disturbance to output. And this is the resulting transfer function. I will not tell you how to do that right now. You can try to derive this result by yourself, okay? If you don't do that, that is okay too, because we will go back to this equation in the later part of this course. But for the time being, I just want you to know the utility of block diagram, how useful it is, okay? And I want you to know that node is typically more than one input for a feedback control system, okay? This is the standard input, so-called reference input. And this is, of course, undesired input because it is a disturbance. Unfortunately, no matter how undesirable it is also more often than not unavoidable, which means it is always there, okay? Now, here is a number of figures which illustrates block diagram transformation. For example, let's say this is the original block diagram, okay? You can transform it into this simplified form, okay? So this is the resulting transfer function. Note that whether or not this sign is positive or negative, depending on the sign we employed, okay? If, let's say, we choose this sign to be negative, then we have a negative feedback system. If, on the contrary, we choose positive sign, then we have a positive feedback system, okay? Positive feedback system do exist in the real world, but for most of our applications, we always choose negative feedback. Why? Because it makes sense. Why does it make sense? Because we want to input to the controller to be output error related. So we need to find a difference between the target output and the desired output. And that can be only achieved by using negative feedback, right? Okay, now, another good thing about block diagram is that by using simple block diagram manipulation and by using simple algebra, we can actually simplify the representation of a system. Let's say this is a block diagram of a real physical system that we need to manage, okay? Very complex. You have 3 feedback loops, okay, occurs in different parts of the control system. And no matter how complex it is, I still need to determine the transfer function, the overall transfer function of this closed-loop feedback system, which involves 3 different feedback paths, okay? So how do we do that? Using the technique which we call pickout points, all right? So the first thing you need to know that to use this transfer function, what we will use is this block diagram transformation techniques. To go from here to here, we need to make sure 2 things. That is, here, this is a feedback loop control system, right? It can only have 1 input and 1 output, okay? Now, this is not the case here. Here we have a feedback loop, all right? But it actually has 2 outputs. One is here, the other is here. So we cannot directly transform this into a simple feedback control system. We cannot use, where is this? I'm sorry. My bad. We cannot just directly use these transformation techniques, okay? But what we can do is that let's, instead of the feedback loop of this feedback loop, instead of feedback here, you can move it one step further to here, right? Okay. Once you do that, the good thing, the good thing is this become a standard closed-loop feedback system because now it has only one input and only one output. All right, single input, single output, very clean and simple. So let me replot this diagram here. Okay, the only thing I do to go from this diagram to this diagram is I replace this portion of the block diagram by this. How do I do that? By using this simple block diagram transformation technique. All right? I can do that because this is a very standard feedback control configuration, one input and one output. Now, we need to go one step further, okay? So, let me replot this here. Again, this is a standard feedback control system because it has only one input and output, only one output. So the transfer function from here to here is actually this. And again, this is a standard single input, single output feedback control system. Again, by using the same transformation technique, we can come up with the final transfer function of this model. Okay, pure and simple. Okay, very straightforward. No, nothing fancy. Okay, the technique is so straightforward. Okay, you look at it once, you know how to do it. Please do it by yourself. Okay, something I don't want you to think. Okay, when I was a student, my professor or my teacher told me to, hey, Vincent, go home and practice. And I always respond, why do I have to do that? I think I already understand. I don't need to practice. But when I go into the final or midterm exams, when I see similar problem, I laugh in the beginning because I know how to solve it. But when I actually try to solve it, I discovered that actually I don't know how to solve it. Okay, I just think I can do it. But when I really try to do it, it's not the case. Okay, and it is too late to find out this terrible fact. Okay, so don't repeat my mistake. Okay, try to do it by yourself. Make sure you know how to solve the problem. So don't feel sorry. So you won't be sorry when you take the exam and find a similar and encounter a similar problem. Okay, all right. Now let's go to another next important topic, which I consider to be the most important topic of this course. That is, we want to study frequency domain analysis. And this is actually divided into two parts. The first part is frequency domain analysis for signals. The second part is frequency domain analysis for systems, because a control system is made of system itself as well as inputs and input and output. And input and output of a system are always signals, okay? And typically signals are function of real time. All right, now let's go back, review this Fox oscillation of a spring mass damper system. Remember this diagram? Remember this plot? Here, this equation of motion represents the spring mass damper system itself. That is why we often call it equation of motion, because it governs the moving pattern of the motion of the mass. So sometimes we also call such, okay, 10 o'clock. Let's take a 10 minutes break and we'll come back 10 after 10. 谢谢。